moving. So we understand the thing, and we have to implement it now. So what do we have to do? We have to, I guess we need to like add extra parameters, for, like we need to like remember extra stuff for each weight, right? For each weight that comes in, we have to track this like moving average parameter as well as this variance parameter. I think betas are hard-coded and alpha is hard-coded. So for each parameter that we're tuning, we need to remember these extra things. Also, apologies, chat. If I was ignoring you a little bit, it's because I wanted to make sure that first part was like succinct and postable, but I'll pay more attention to you now, I promise. I promise. Thank you again, Leo, for the 10 gifties earlier. I didn't want to make much of a big deal about it for the same reasons, but I do much appreciate it. Okay, so we need to like remember extra stuff. After we do that, we have to probably like write kernel to apply these things, to like apply and update, and then I guess like test, right? But other than that, I think that's kind of it. Okay, so let's get moving. I guess this is like 2355 plan, and then we have now let's start implementing. Okay, so in the context of our guy, we have neural network.zig, and as part of him, he has an optimizer who calls optimize on the gradients, and this is where all like the work is done. So this guy, I believe, when we set up our optimizer, maybe in main we set him up. Train thread maybe. When we set him up, I believe we like loop over all of our layers and register their weights at the optimizer. So this is probably when we should create our like extra data, right? So like instead of just holding like the weights for our parameters, we actually have like some extra stuff to hold now probably, right? So we're gonna have like weights, or like, yeah, weights here, which is a GPU buffer of stuff. And I guess we will hold like extra params. So we can call this, maybe this is atom params or something. We're just gonna hard code atom in for now. Maybe later we can kind of have like a how to say this? Maybe later we can have like an interface for an optimizer where we can implement different guys, but for now we'll just throw atom params in here, and we'll kind of define those parameters all in GPU land, I think. Now our weights now here is like items here, and when we register these things, we're going to have to say weights is this thing, and we're gonna have to like create an extra tracking guy. So what do we do here? I guess our parameters here are what? We have M and V, which we just both initialize to 0, right? We don't have anything that needs to be like constructed in some specific way. And so we could honestly just like define the packing here, to be honest. Let's just write that down. We'll say, what is that you're drinking? It's a black instant coffee in a beer mug. What part don't you understand? So we need MV, MV, MV. In Canada, you just use normal units like metric system. Yeah, for the most part, we're pretty like infected by like America in a lot of ways. So we for height use feet and inches, and sometimes for like lumber, I don't know if lumber I assume gets like that treatment around the world, right? Because like you just have like standard like widths that are in inches, and like they probably make less sense in millimeters. But you know, for the most part, for the most part. It's, yeah. Specifically height, we use imperial, but for a lot of everything else, we use metric. We might use, occasionally, I hear people talk about pints in ounces as well, which is weird. We don't really use milliliters for like beer size, unless it's in a can. We use milliliters for beer size in cans, but not in mugs. Okay, Adam Param. So this is going to be Schmitty. Thank you for the 10 gifties. This is much appreciated. Thank you so much. This is very generous. Okay, so here we need to like create some GPU buffer, which means that this guy, he has an executor here. So we can actually just say like, executor create tensor fill. Do we fill this shit with zeros? This guy needs an allocator. Okay, to like put this thing on. Not sure if we want to inject that here. For now, I'm gonna just put this as a parameter that he holds. I'm not sure if this is actually what I want. Fix me, decide if this should be a function parameter. But in terms of like implementation, this is easier for now, so we'll do it this way. And then we set the dimensions of the thing that we're doing. So this is going to be, I guess, 2 parameters per weights num lms or something. Maybe we just put like consider it flat. Because in reality, it doesn't really matter what the shape of the input is. Okay. Maverick, thank you for the prime. Much appreciated. We're going to keep the streams going till you're 80. Let's go! Never die. Live forever. Okay, what's this mad about? We probably have to say what we're filling it with. Zeros. Okay, and then this guy's mad because... What? Well, okay. I want to know what this guy's mad about, but we have to get to that one, so here we go. Okay, so he's mad because... Oh... Tracing executor. Okay, so we actually want, here... So we have, tensors that are... We have, like, a generic tensor type. And he might be, like, a representation of ND data, like n-dimensional data on GPU, but he also might be a representation of n-dimensional data in execution graph. Right? So that's kind of like the difference between the traced version and the non-traced version, is that we have like a guy whose job is to like look at the math we're doing and write it down. And so all we have to do here is just like convert. So we have traced, we can say like get the underlying GPU buffer for this guy. And then we pass this in here instead. Why do I need this? Am I stupid? Oh. It's because this guy, sorry, this guy is just the other type. So this guy's untracked, this guy's tracked. That's what we want. Cool. Okay. So now when we run the optimizer, we probably want to do something here where, okay, so first of all, this is like item weights buff now, weights buff, and then this is item, I think we're chilling. Yeah, okay, so this like works now. But we have to probably like, before we were composing, multiply this thing by the learning rate and then like scale and then like do like an add assign of the gradient to the weights now. I think we probably want this to be like a thing, like a kernel that executes on GPU now. So this guy needs to own like, you know, Atom kernel. He needs to own a compiled thing that he remembers for later. So I think we're like CL executor kernel like this. And this means that this guy probably wants to start like initializing himself properly. And I guess he is going to take all of these things, almost certainly. Which might be better as like pub const init params when we have so many. kind of nicer to have them as a structure. Right, and so here we have like params, init params, and then we just kind of copy paste most of this stuff from our init params. Just like put a dot here, yank till the colon, find the colon, equals paste params dot, find the colon again, and then go to the next line. Okay. Now all we need is to like compile our kernel. So let's say that we have the Atom program content is going to be like some embedded file of like Atom CL or something. Sure. And what we're going to do is we are going to do like a compile program, create program. So this is going to come from Atom program content. Then we're going to have kernel. Holy, Alex, thank you for the 20 gifties. You guys are fucking going crazy today. What the fuck? That's insane. Thank you. That's a lot of money. So thank you. That's very kind. Very kind. Yeah, thank you. Thank you. Okay, so he's going to extract out the Atom kernel here. Maybe just we'll call it Atom inside. And then here he's just like Atom kernel is equal to Atom kernel. And then presumably we need to like run this guy. So instead of doing whatever we were doing before, we just take in, you know, the gradients and the tensor, and I guess we figure out what to do here. So it's like self executor, execute kernel. His output is going to go somewhere, I guess. Why? Oh, untracked maybe. Here we go. And he's going to, what does this guy take? He takes in the kernel, so self Atom kernel pipe. I guess we're kind of in here, huh? He's going to take in the kernel. He's going to take in the number of things that he's going to run here. So I guess we are updating, like, for each weight that we're updating, we have to update each weight. Bro's stuck in the matrix forever now. Yeah. Live forever, never die. So I guess, like, this is the tensor num dims num elements. And we probably are going to have to pass in some stuff to this guy. So we probably want, like, the gradients. Probably, like, the thing we're updating first. Then we have, like, the gradients that came in. We also want to have, like, our extra parameters. So we'll call this, like, self add we need to look up. It's like Atom params or something buffer here. We probably want the learning rate. Holy jeez. Another 10 gifties from Leo. Guys, cool it. This is a lot. This is like this is like actually starting to be like more than a minimum wage job at this rate. That's crazy. Thank you so much. Thank you so much. It's very kind. What else? What are we fucking doing? We're passing in buffers. We also want, like, our multiplier, our, like, learning rate, probably. And we'll figure out, I think that's most of it. Also, like, we need to pass the number of elements again. Yeah, but Canadian monies. Yeah, it's like Monopoly money over here. Okay. So I think that if this works, then we're kind of chilling. Oh, we have batch size here. We're scaling the learning rate according to batch size right now. We probably want to keep doing that, I think, because usually your loss is scaled by the batch size, and our loss isn't. So I think that we do want to use that here instead. Sure. This could be negative or positive. Doesn't really matter. Okay. Does GitHub take 50% like Twitch on the sponsor thing they have? I don't think so, but I should know the answer to that hands down, but I'm pretty sure on GitHub I get like almost all of it. Pretty sure. Okay. What are we doing? We need to now add this like atom.cl, who has a kernel in him, who is going to say atom, and he has to take all the parameters that we just said he took. We did it in the wrong place. No, it's okay. It's okay. You guys the people who you gifted subs to get something in return, which is great, right? They get access to VODs. Twitch uses a signal boost, you maybe know. Yeah, I'm sure that I wouldn't worry too much about it. Man begging for money. I wouldn't worry about how you waste your money. It's just like, shut up, me. According to AI Summer, GitHub takes up to 6%. Yeah, it's like way lower. Yeah. I figured they took something, but like almost nothing in comparison. Okay. So I guess here we'll just write down what the parameters were. Sournux, thank you for the prime. Atom CL. So here we just copy paste these parameters and we convert them here. So this is going to be like, can I do set shift width equals 4, expand tab equals 4? There we go. So here we have global memory float pointer to weights. Here we have atom params here. Here we have gradients. And then we have uint. Oh, this should be a float here. Gradmol. And I guess we can call this, yeah, uint in Gradmol, we'll call this an n. Okay, we gotta fix that to be a float here. Easy. And what do? We have all the information here. So we're gonna hard code constant. It's like float beta 1. I think that they have this hard coded at 0.9 and beta 2 at 0.999 or something. Let's double check. The paper 0.99. Yeah, so they hard code beta 1 at 0.9, beta 2 at 0.999. We could pass these in, but this is fine. And then while we're here, we might as well take in epsilon as well. So epsilon here is 1e negative 8. You guys think you have Monopoly money? Do I want to click this? Trading view symbols? I'll open it over here first. And then... Oh, you're comparing to Turkish? Yeah, that is a lot worse than the Canadian to US. Okay. What am I doing? We're implementing this. So we got... I guess we'll do like a global float pointer to M is atom params times global. This is like plus global ID times 2. So there's 2 parameters per weight. This is get global ID. And then we have to like bail out if global ID is greater than or equal to N. Okay. Cool. We have a V here as well, which is going to be M plus 1. Right, in this language, the pointers are like plus 1 is in float space, not byte space. So I think this is right. Cool, so we have these guys now. So we say M is equal to beta 1 times M plus 1 minus beta 1. Times gradients at global ID. Easy. This is this. Okay. We do V with beta 2, and this is gonna be, maybe we'll do this. Float grad is this. So now we can do grad here and grad times grad here. Easy peasy. Then we have like m hat. So how do we handle this? Because I think we probably actually want to store this like beta to the power of t as well. Actually, it's like what is like higher cost here? Recalculating this with a power call or remembering the last one? I think power is relatively expensive, but memory is also relatively expensive. So I'm going to bet on the fact that we should be using time step power here. Can we like implementation of pow function? Is this like just a loop? Like, are they doing something like intelligent, or are they just literally going like 4-0 to exp? Okay, let's look at a floating point pow function. Like, what's our like fucking big O here, you know? Use libm pow function? Yeah. Libm pow. Like, I want like, what's the word for like big O? I want to know like complexity. Constant time. Oh, nice. Okay. But I guess like we should check on GPUs. Do GPUs have built-in pow function? All right. Sure. Sure. Okay. I'm willing to try it at least. So here we're gonna be like, B1T is, why is this mad? Oh, probably because this isn't finished here. So this is pow F, or maybe just pow in this language. No, wait, why is this, what is going on with the highlighting here? That's very strange. Oh, float here? Huh. Am I crazy? Uint T. Uint T. Why? I don't know why this isn't highlighting. That's very strange. But we'll come back to it later. I'm sure we'll see some sort of compilation error. So it's just pow B1 to float T and B2 to float T, and then this is float B1T is this guy. That's what you get for not using Emacs. My bad. Okay. Cool. Easy. And so we have like m hat is, you know, m over 1 minus b1t, easy. V hat is v over b2t, easy. And then our output here is, we need alpha in here as well, which I guess is just this, what we're calling this. This is alpha. So maybe it shouldn't be scaled with batch size, actually. I'm not sure. So weights at the output ID is equal to previous minus m hat over squirt v hat times alpha. Hype. Is that it? So maybe. So we need to adjust our like caller of this guy to, we're gonna make alpha a parameter here. I guess we'll say LR is alpha. So I think we're just gonna do self LR here, and then we need time step here as well. And I guess here we have T is a U32, I guess. And then here it's like defer self T saturating add 1. And we pass self T here. All right. Sure. Batch size now is not used. We'll just comment out for now. And then this guy wants Atom kernel. So this guy wants to call try init with this stuff now, which should be mostly free. This guy's mad because we need to initialize T to 0. True. And then this guy's mad because this guy is not taking himself by mutable reference. But otherwise, we're kind of chilling. So does this fucking work? We NAND off rip. Probably because our default learning rate is now like way too high. Let's just make this thing like really small just to see. We might also just like fuck this up big time. Yeah, we are. We forgot to add the epsilon in to the bottom of the division, which could be immediately nanning us there. No, okay, so let's take a little bit of a closer look here. If global ID is equal to 0, can we print something here? Printf W is weights global ID. We have M hat, V hat, alpha. And we probably actually have to print the numbers associated with these things, huh? Alpha. What are we fucking doing wrong here? Weights, global ID, M hat, V hat, alpha. I forgot this. Is there a way to do printf like this in GL shaders? I think so, but I don't know what it is. M hat infinity. Interesting. If it's good enough for Karpathy Sensi, then it's good enough for us. What are you talking about? Is this in response to something? Or are we just linking? Well, I don't want to read this right now. What's the context? I know you're into Zig neural networks. Have you looked at Language Mojo? No, I haven't really. No, sorry, irrelevant. Okay. Maybe I'll take a look later. Okay, so M hat is infinity because B1T, this means that B1T must be too close to 1? I guess time step has to be at least 1, right? Because this to the power of 0 is 1, which means this is 0. So we have to have time step of 1 off rip. Okay, so this is better. We are still nanning immediately, which is surprising. Because now these, wait, hold on. Was V hat seems valid? Alpha seems valid, but maybe there are cases where we're not valid for some reason. Can we printf the output weight as well? Output. This is going to be weights global ID. So regarding math ops, do GPUs have specific hardware instructions? I think so. But it could be that they have like intrinsics that get compiled to like a more other options. Not really sure. So this seems okay at the very least at like the first input. But we are seeing nans all over the place. So it could be that our learning rate is too high. That's an option. It could be, okay, let's look at if weights global ID, if like is nan, can we start freaking the fuck out? Panic, panic, panic. Freak the fuck out. Okay. Interesting. What's happening there then? Panic, panic, panic. Weight is nan. And our M hat and V hat seem pretty reasonable, no? So that means that the input weight must have been invalid? Right? That's the only other input here. Oh, it could be that the gradients are nan. Yeah, wait, hold on. No? Okay. Can we do previous weights? Is weights global ID? Am I crazy? Dude, why is he freaking out then? Can we do like a jump text? Oh, oops. Okay, let's give him a sec. So the first thing that goes wrong? Oh, I guess V hat is negative. Are we square rooting V hat? We are square rooting V hat. V hat should never be negative, no? Because we have... Oh. I used M here. My bad. My bad. Oh, wait, wait, that's training. Okay, hold on. Let's, get rid of this shit that we don't need now. And let's try cranking up the learning rate a little bit. So this is already... Holy fuck. Holy shit. It's actually getting so... Oh, wait. Maybe that's not crazy. Hold on. Can we compare git stash? So what does this look like initially? So initially we got down to like 6,000 very quickly, 5,500-ish. And then it stops making progress. So it looked like it was moving very fast, but it was just moving very fast to where we were before. We have like an extremely low learning rate now, I think. So let's crank that up a little bit again. Git stash pop. Okay. So bring this back up to like what it was before. Let's just kind of see how this plays out. Okay. So if he like immediately makes it past this like 5,500 barrier, which he did, right? He immediately, oh, that's beautiful. And oh, that's actually so good. We can probably crank this. Not too high. But let's see what happens if we like double it and give it to the next. Let's see if we like converge on something that's like pretty okay pretty quickly. Yeah, okay, we're down to like 3,000 pretty quick. 2,000, yeah, this is incredible. This is way faster. So now we can immediately start looking at our outputs here and like see if they're like already pretty good. So like that's pretty good, right? Barcode here. That's pretty good already. Oh my god. This is actually like, that's awesome. It's actually so much fucking faster. This one, it didn't figure it out, but sure, like the data it's trying to compare against is kind of hard, that one. This one's also hard. Okay, so if we wanted to see how long it took to get to like 2,000 with the old way. Oopsies, fuck. Oh, fuck. What did I just do? I tried to, okay, get stash. So the old way, like, how long are we talking to get to like 2,000? We should time this actually, right? And then we'll close it when we get to 2,000 and we can compare. So you raise the bar bracket code. Good one. Yeah, see, here he gets like stuck so quickly. So this is also like consistent with I'm gonna kind of keep this on top so that we don't lose track of it. But this is consistent with these graphs from the Atom paper, right? Where like these ones, right? Where we are doing like a worse version of SGD Nesterov here, and we kind of are seeing this, right? Where we have like a very slow initial train, and then like it kind of like gets better later, where like Atom immediately goes like boom, gets better like quick over time. So that is what we're seeing. Look, we're still not close, right? We're still at 4,000. Like amount of time to get to 2,000 is like crazy. For the same loss, SGD tends to generalize better, but nobody got time for that. Yeah, fair. So if we look at like the later outputs here, like we can still see he's like less confident, right? He's still not really getting like reasonable masks. Like 4,000 loss is like not that good. You're talking about though that like Atom, you would see on this data, SGD and Atom, we should see like approximately the same maskiness for the same loss value. But with SGD, you're saying that like when we start feeding it data that we didn't train on, it gets better. Yeah, so we're still like not even close, right? We're like 4,000 still. So that was after like a minute and a half. If we compare that to like the Atom way, so let's see, we're moving down. So here already, we're as good, right? 10 seconds versus a minute and a half, we're like at the same point, which is crazy. That's actually insane. And then we can like see how long it takes to get to like 2,000 as well. But like that's fucking sick. So like, yeah, he's already passed him. That's crazy. And if we look at like the outputs, they're already getting more confident, right? You can see like this is like those are very confident results in comparison. Some of them he hasn't figured out yet, but on the ones that he has, also the output confidence might be more calibrated with binary cross entropy rather than MC. Yeah, understood. We're not really, yeah. We should probably be doing binary cross entropy, but I guess our learning rate's a little high because he just NAND. But that's sick. That is sick. Okay. Do I want to do more today? I didn't really think this one all the way through. I was like really focused on making sure that I like nailed the Atom intro, so I didn't really have like other stuff I had on the like in my mind that I wanted to accomplish today. So maybe we could say short stream today. You know what? It's Sunday, short stream. We'll be chill, you know? I guess it's kind of rude to take your guys like 40 gifted subs and then immediately quit, but sorry. I didn't plan for that. Happy with that. I need to think about what's next. It's probably trying to train something that starts doing like actual barcode detection. But I have to think about it. So thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 Pacific time. We usually go a little longer than this, but it is what it is. If you want access to, if you want to watch stuff that you didn't see live, there's a YouTube link in the Twitch description. Some of the stuff goes up there, some of it does not. Probably everything from today will go up there. I think what I'm going to do is I'm going to segment today's VOD for the intro segment, and then probably just post an unlisted second half that's linked from the first. I think that's probably what I'm going to do. But sometimes we do we get a little crazy with it, and we post things on like Patreon or YouTube members or Twitch. The Twitch VODs are accessible for people who subscribe. So if you want access to like the total content, sub on one of those platforms. But if not, obviously no pressure. So cool. Thanks, YouTube. Peace out, and Twitch. Let's find someone to raid.